Here is the flip. Here is the flip. Test.
Hello everyone, welcome to String Seminar. Today we have Semanti from IMSc who will be talking about exact RG and holographic RG.
Good afternoon, everyone. First of all, I would like to thank seminar organizers to give me opportunity. Today I will talk about exact RG and holographic RG. Here. Okay. So this is a work done with Bala Satyapalan and Pavan Dharani Pragata. We are all from IMSc. Okay. First, I will tell a brief what we are trying to do. That is, in ADS CFT conjecture, what we do is we perturb a boundary CFT with the operator JX OX, and the JZ of the CFT can be calculated using action of solution of equation of motion in bulk theory with boundary condition JXZ is equal to JX. So now if one consider a ADS space in Poincare patch, that is given by this, there is 1 by Z square factor multiplied in the metric, and boundary is at Z is equal to 0. Now instead of putting boundary at Z is equal to 0, if one put boundary at Z is equal to epsilon, one can see that 1 by Z square acts as a scale of the boundary theory. So scale of the boundary theory changes. Now evolution of Jx epsilon at Z is equal to epsilon, that comes from the equation of motion of bulk field in ADS space. Now holographic RG is, in short, from UVIR duality, one can tell that how Jx epsilon changes with epsilon is related to RG equation of Zj in the boundary. Hence, one can tell that RG equation of Zj in the boundary should be related to equation of motion of bulk field in ADS space. So the question is, what is the precise connection between these two quantities? Now, plan of the talk is, so first I'll tell that how people do different schemes of holographic renormalization. Then I'll give little bit details about exact RG, and then how to obtain free scalar theory from exact RG equation, free scalar theory in the bulk from exact RG of the boundary, and then how to obtain gauge boson action leading turn from boundary conserved current. At the end, we'll give some conclusion. Okay. Now holographic renormalization, holographic renormalization is that in ADS CFT both side needs renormalization, while QFT side have UV divergence, gravity side have IR divergence. So one scheme is finding correlation function or beta functions or QFT using renormalized gravity action. So this line of work has been done by Henningston, Skendries, Harrow, Skendries and his all collaborators in 2001 and 2 years. A more clear picture about relation between holographic renormalization and RG, Wilsonian RG, is given in the paper by Faulkner, Liu, Langamani at 2011, where they are writing in bulk, this bulk action, they are writing, decomposing in two parts. One is this part, which is completely of, belongs to bulk, and this SB 5 epsilon, where epsilon tends to 0, this one can see as a boundary action where boundary is at Z is equal to epsilon. So one can see that as a boundary state where the modes, which is where Z greater less than epsilon has been integrated out. So this I'll come by picture in the next slide. So, and in the boundary on the other hand, I effective is Wilson action or low energy effective action at scale lambda. So we'll see these details in ERG essential part. So in this paper, they are interpreting this SB as I effective. So if one does that, then how SB changing with del epsilon that they have shown is is given by Hamiltonian of radial evolution, and this they are interpreting as RG of the boundary. So this is coming from UV-IR duality. Yeah. So all these things in the Faulkner. So this picture I have taken from Faulkner itself. That suppose we have boundary and bulk picture. So when our Z is at, suppose our Z epsilon naught is the highest value it can take, and in the boundary lambda naught is the scale of the theory, the UV cutoff. Then if one can integrate all the modes from epsilon naught to epsilon, that state correspond to in boundary all the modes which is integrated from lambda naught to lambda. So we will see correspondence between this this connection between these two things. Okay, so this is the rough picture of like holographic renormalization and connection between RG evolution. Now we are using exact RG for our purpose. So for that I will talk some details about ERG. So ERG is first of all renormalization group evolution. Instead of looking at old way of seeing removing infinities from correlators, it can be seen as process of changing scale. So change in scale from lambda 1 to lambda 2 means integrate out modes between lambda 2 and lambda 1. But when one integrate out high energy modes, that results in irrelevant terms in effective action. Irrelevant terms means the negative mass dimension terms. So when lambda naught, usually when we are in continuum QFT, this term does not appear, but otherwise these terms will be there. So in ERG, what is special is that the suppressing of high energy modes is done with analytic cutoff function. So this results that when we calculate a correlator in new scale lambda, that can give back old correlator so that no loss of information is there. So whatever I told here, if I tell mathematically, that looks like I start with a bare theory whose scale is lambda naught, where usually kinetic energy term is p square phi square. Here we have put an analytic cutoff, and this is the interaction term. So analytic cutoff is chosen in this condition. It tends to 1 for x tends to less than 1 and 0 for x tends to infinity. Now one decompose phi in two parts, phi L plus phi H, where phi L will be propagated with propagator delta L here, and phi H will be propagated with propagator delta H here. Now if you combine these properties of Kx, you can see that phi L will propagate only modes which are less than lambda, and this will propagate modes which will between lambda naught and lambda. So this is called low energy propagator and high energy propagator. So now work is to integrate out the phi H. What we remain is we need to integrate out phi H. This is the action. This is the action we are left with. That will contain that non-trivial irrelevant terms mentioned before, and this total partition function will be integration over low energy modes. So this S lambda is called low energy effective action or Wilson action, which is given by this expression, where S I lambda are those non-trivial irrelevant terms, interaction terms will be there. And now you can see from this term that this new theory is at scale lambda. Okay, now if we got S lambda, one can ask question how S lambda changes with lambda. So that is given by Polchinski equation. So we have introduced a new denotion, that is T, which will interchangeably use for scale. T is minus log lambda by lambda naught. So in many ways you can write RG equation. You can vary S with T also. You can vary generating function with T or effective action. There will be different kind of equation, but for our purpose, we are using Polchinski's equation. So this is the Polchinski equation. So first of all, I would like to draw attention in this. This is the most simplest part of the equation. That is, if there is no interaction, nothing, this will give the engineering dimension of the action. And then the main structure of the equation is given by this. So this is the, okay, before that I will tell, this is the part, eta is the anomalous dimension, and the thing which are multiplied to minus eta by 2 is the number operator. Now what happens is, whenever we change a scale, every time dimension of the phi also, like effective dimension of the phi also changes. So we have to change scale in such a way so that every time kinetic energy is standard. So for that, usually in QFT, what happens is, if you do a field redefinition, you are left with some term proportional to equation of motion operator. Here also same thing happens, but there is this new thing which is coming from the fact that we are now not at continuum QFT, we are at general S at general lambda. So these terms are proportional to composite number operator in ERG. And eta by 2 is anomalous dimension.
Why do you call it number operator?
Because in classical equation, this is number. So if you consider a general phi, general lambda, this new terms comes. Like this is for continuum QFT. If you for, so this is the main structure of this equation, where this part, as you can see, is I will show in next slide that this gives a non-pi part, and this part gives both pi and non-pi part, and somehow by cancellation one can find anomalous dimension or beta functions, etc. So here in this equation, all variables are made dimensionless. After that, if we say del S del T 0, that gives fixed point action. And another important thing is this k prime p square, which is related to low energy propagator delta. So one can do calculation with general kp, but for ease of calculation, sometimes we choose kp as e to the power minus p square. So all the p square here is actually py lambda. Okay, so by p, I could not hear what.
What is n phi and np over there in the classical dimension?
Oh, n phi is number of phi's and a number of p's, like phi dot phi del del phi, p del del p. Okay, so in picture one can see that there will be non-trivial irrelevant terms when we integrate our high energy modes. So in continuum QFT, what happens is the change happens. Suppose I want to find beta function of 4-point correlator. So it happens is that like we are changing infinities in the 4-point correlator. Here it comes in a different way. Here when we integrate out high energy modes, this 6-point vertices come in the effective action. Now this 6-point vertex, if we put in this term, this gives rise to two kind of diagrams. One is this and another is this, like contraction between phi's of two side and one side. And this one can compare with this part. These have typically contribution like you are taking a contact diagram and del del phi of that, and then it is a first order correction to propagator and del del phi of that. So in low energy momentum case, this thing and this thing cancel. What remains is these things, and this gives beta function. So that happens in continuum QFT also, that these terms are logarithmic divergent terms. By adding counter terms, one gets beta function. So if one to find anything from Polchinski equation, if one goes by Feynman diagram interpretation, it becomes easier. Okay. So in our work, we need only this Polchinski equation, that in more simple form. Okay, so now I will talk that how to derive ADS free scalar action from boundary CFT using ERG. So this is a 3-step procedure. First is write Polchinski-Yargi equation for d-dimensional boundary theory. And then write evolution operator for Yargi equation as a functional integral over a d plus one dimensional field theory. Now after that, to make it come to a form of ADS space, we do some field redetermination and change of variables so that it looks like d plus one dimensional ADS space. Okay, so this is like, yeah. So how to derive bulk action from Polchinski equation? First we consider, so this work has been done by Bala Satyapalan and Hidenori Sonoda in 17 and 19. So consider perturbed Gaussian action. So we are perturbing around this Gaussian action with SI. Note all variables are dimensionless, and we define a variable psi e to the power minus SI. Now if we consider most simplest case of Polchinski equation, there is no anomalous dimension or anything, then this reduces to this form, where G is related to G is K, this analytic cutoff function by P square. Okay. So if you look at this equation, then you see this is like a diffusion equation, and then one can write evolution operator of this equation, which is just exponential of integration over H. Now with this evolution operator, one can write in terms of functional integral the connection between psi of Ti phi I and Tf phi f, where phi I and phi f's are the boundary conditions at Ti and Tf. So this is the usual path integral expression. We want to interpret this as holographic Yargi equation, in the sense we are deriving it from boundary Yargi, but this corresponds to some theory in bulk. From bulk perspective, you can think this corresponds to some theory at some scale z is equal to epsilon I, and we are doing evolution with respect to some bulk Hamiltonian, and then it is giving a theory which is at scale z is equal to epsilon f, for example.
In the previous slide, if you can go back to the previous slide, you are neglecting nonlinear terms in psi. You're only considering the linear terms in psi. Is that what you are doing when you think of it as a perturbation? Why? How did it? Yeah. How did?
No, actually, if you see this Polchinski equation, is in terms of S. Na? Here, if you put psi, that comes in this part comes in that form.
Okay, and then you neglected all the other terms.
Yeah, actually, anomalous dimension we are neglecting. That requires separate treatment. We just want to show free scalar field for this anomalous dimension. Sorry.
So that's what I mean. So in a sense, you are treating the SI as infinitesimal. I mean, so you're neglecting higher order terms in SI. Isn't that? I mean, I'm trying to understand what is the approximation you're making exactly
in this equation.
Yeah, to go from the top equation to the bottom equation. What is the? Is it like you think of a perturbation parameter outside SI and then you neglect, but that doesn't seem to be what you're doing.
No, we are choosing, suppose we choose SI in such a way that Polchinski equation in this form, then we can see that we will, then this will turn out to be free scalar field in SDS.
That may be later, but I just at the level of the Polchinski equation, I wanted to understand
so
what approximation you're making to simplify it to that form.
Yeah, one thing is this term we are not considering. We are not considering anomalous dimension because, for example, we want to prove free scalar field theory. There is no interaction in that sense. And then this.
But this is in the boundary, right?
Yes.
So, yeah. You have a free field in the boundary and a free field in the bulk. Is that the one?
No, there is no. We are perturbing the theory. Then, but if we take epsilon this eta 2, that will give suitable correlators like 1 by p to the power 1 by eta. But we just want to show the simplest ADS free scalar field. So for that, we don't need eta.
Where did you use the fact that you have a CFT on the boundary?
CFT, oh, no, that is like we are perturbing around a CFT, like Gaussian CFT.
Yeah, free theory.
Free
It's a
theory.
free theory which will be a safe.
Okay.
So in the UV, it will be asymptotically ADS.
Yeah.
I see.
Yeah, so I mean, normally you would perturb it by saying, like, let's say eta is proportional to some coupling constant, and you set it to 0 when you're in the limiters. But that would seem to require then. What I don't understand is the perturbation the variable you're defining is e to the minus si, right?
Yeah.
So that's not a systematic expansion in perturbation as far as the perturbative parameter. If I imagine putting a lambda in front of the si in the first line, if there's a lambda in front of the si or in your action, which is the perturbation parameter. Yeah, and take lambda to be small. Then that is the usual perturbative expansion, but that doesn't seem to be what you're doing here, because you are not expanding in lambda. Your psi variable is e to the minus s.
Yeah, this is the full interaction term. I am not doing perturbation here. Like SI is the full term.
But then why? What is the justification for dropping the eta term? Because the eta term is proportional to lambda also.
Yeah.
Why are you dropping that term as opposed to other terms?
Like, if you take eta, they are required separate. I'm telling that requires separate analysis. I just want to show from here that with this simple thing, we can derive that free scalar field theory without anomalous dimension.
So when you say consider pot or Gaussian axis,
yeah,
you're not thinking of SI as small elements. Is that right? I mean, it is in what sense?
SI, see, here it does not matter. But if we take gravity, maybe that time this back reaction, these things matter. But for this theory, I don't think, yeah, SI, you can take any value.
I guess the question is, does SI cause eta to be non-zero? Because in general, SI will make eta non-zero, right?
Right.
So that's the confusion, that there is that eta is 0, but SI is non-zero. How is that consistent? That is the question. Because in general, SI and eta are proportional to each other.
Yeah, that is true. Means what, as far as I understood, it is like with eta also you can find, 1 minute. See, if we incorporate eta, then there is a separate analysis you have to do and you will get consistent theory from there. In this analysis, I just want to it, there is no eta or anything. We can derive free scalar field.
It's in mathematically inconsistent. That you agree.
Yeah, means there will be other terms with this.
No, but if SI is non-zero, then there should be in general.
Yeah, that means, yeah, that I agree. Like that will be like maybe other part, like plus this, or these correlators will change actually. Like usually what happens if there is eta, there will be 1 by p to the power 1 by eta. But here it will be something like 1 by p. In that sense, you are giving just the leading term.
Yeah, anyway, maybe you can go ahead and come. So this evolution operator you're writing from the, so let me see.
These are just a path integral.
The path integral, and your g of p at time tf minus g of p at time ti del squared. Okay. And then you're writing it here as.
So this t is your RG parameter.
Yes, t is scale.
And you are thinking of, so this evolution operator is in gravity, is that right?
Yeah, so we were to interpret this as D plus one dimensional field theory. And now there is an extra dimension dt, which we will see that we can connect with Z of ADS.
No, what I'm confused is that you introduce this U,
Yes,
right? So that H is H of what? This is the H of the
H
CFT.
of, no, sorry.
At this stage, you
here
can
this-
interpret it as the
this
H
as
here.
H.
But
It's a
if you
diffusion.
interpret this as del psi, del
I
T
see.
is H times psi. It's a linear. And that's why the G dot gives you the G of P at time TF minus G.
And then eventually that will become the radial coordinate. Is that the point?
Yes, T will become radial. Okay, so what we will show is like this is correspond to bulk radial Hamiltonian. And this is not in recognizable form because there is non-standard kinetic term. So we have to do suitable field redefinition and change of variables. Okay, so this is so after this, this is quite straightforward. That we find from this path integral, we find the action, the evolution action, which is given by this form. Now we adjust G dot in such a way that it takes this form, and F is the new variable. Now we do field redefinition, phi p as yp into F, and change of variable Z as e to the power t, and choose F to satisfy this following constant, so that it looks like ADS free scalar field theory. So if with these three things has been done, then we get free scalar ADS action. So here, yeah. So the characteristics are Yp 1 by F satisfies same equation. So we have some constant on F, and Yp and 1 by F satisfies same equation. So from
Sorry,
that,
can I just see the previous slide again?
Yes.
So you choose F. So F was the thing that was related to G.
yes,
G.
F is G dot. Yeah.
And G is your standard Gaussian propagator, right? I mean, it's the 1 over
Yes.
p square or.
Yes, yes. Related to that, yeah. G dot it is some K prime P it will be, yeah.
Okay. And then you're choosing your F. What does that mean to choose your F to satisfy this equation?
So that it looks like ADS free scalar action. So we're putting a constant on F. This is by hand, yeah.
TDZ is. So e to the minus log F is just 1 over F, and 1 over F is, I thought that related to G of square root of G of B and
This here.
I'm not understanding where is the freedom to choose F to get.
So that freedom, like, yeah, like this. So this is the special constant that will, like, later we'll see that if we choose F in this way, we get correct mass for ADS. In like it is, there is no like when it is a kinetic term with this means in that we are choosing F in such a way that it corresponds to ADS. It has to be seen in that. Like when in field theory, like in ERG also, if you you can choose this kinetic term to certain way, it will just result in some. You can see it is some field redefinition.
So you're putting in that cutoff K.
Yes, yes, cutoff is changed. So cutoff is taking a special value.
So the cutoff function you're taking in a special way. I see.
maybe if I can just ask for a clarification. So you're taking you have some kind of an action for the Kochinsky RG evolution, and you're asking how can you map it to the free scalar in AES?
Yes.
And,
So
and the statement is that
no, how it is like from this statement, like we have a like boundary theory here. Now from the evolution operator of that theory, this one we try to map into ADS space.
sure the RG evolution you want to map it to the
radial evolution
of the
bulk.
scalar.
Yeah.
Okay. And the statement is that you can, but that you're basically doing it by hand. Basically, you're looking at it and you're saying that if you choose your RG time to be some function of the radial Z and your phi to be some in some way with some scaling and so on, then you can write this evolution.
Your G of P. I think the freedom they're choosing is in this function G of P, which has a cutoff. The cutoff function they're choosing in
special
a way,
form.
because the cutoff function will depend on P.
But I thought this is for a general G, right? Isn't that true?
No, G is general G. Like holographic equation here, there is this is for general
G.
If you want to go to ADS form, then you have to choose this special constant. This
but that is not choosing G. Right?
Yeah, that is using, because F square is G dot.
Okay.
Yeah. So
the only question is whether this G chosen this way is sensible from the point of view of the boundary theory. Just from the free theory, is this some G that you choose naturally?
no, naturally means
You will get some Bessel function, no? When you solve
function.
it, probably in your next slide, you're going to say something about some Bessel. I think the question is whether this sort of form for that is natural.
Yeah, it is like if you go low energy limit, this produces correct propagator in boundary theory.
Yeah, he's asking from the boundary point of view, does it give us a cutoff function? Because you wanted K to satisfy some properties, that K should be 1 for low this thing, and then go to like some step function, smooth step function. Does it play that role? Probably you're saying the normalize as Z goes to 0, you're saying no, this is 1 over F.
Yeah, those properties, like from 1 by F, one have to find the G and then they have to check those properties.
How do you determine the A and B? Like, would you set one of them to 0 or?
Yeah, so one of them, as far as I remember, one of them like blows another, I think this one remains, I nu PZ, that remains, and other thing blows off, you go to Z0, PZ0.
So basically you're choosing in the propagator, you're choosing a cutoff, which is like 1 over some square root of Bessel I.
Yes.
Which then decays exponentially at large energies. Integral of.
And at low energy, it becomes a usual property.
Yes.
Because the Bessel I becomes 1.
No, but this F square is proportional to G dot.
Yeah.
And G dot will have actually more like, it's not a step function, it'll be like a delta function. Because you're taking the derivative with respect to the cutoff.
Yes, right.
So you wanted to have a spike. F square should be peaked at some point in the radial direction. That is what you would probably want, because.
Oh, the G is Kp by P square.
Yeah, so when you take G dot, then the T dependence is in K, right? And K has a step function like form. So when you take K dot, you will get a delta function like a peak thing, no? So you want your F squared to have that property, that it is peaked at some point in the Z direction, and then the case.
But Rajesh, you could also have an exponential decay, right? In which
Yeah.
case its derivative will also be an exponentially decaying thing.
For large Z. Yeah. But
At low Z, you want it to be flat. Is that?
that is G, but G dot should be 0. Yeah.
So you want G to be flat near the low Z.
Yeah.
Uh,
But F square is proportional to G dot. So what you are getting as a solution here is Bessel function should be proportional, or its square should be proportional to G dot.
right.
See, G dot will be proportional to K prime P.
Yes. Yeah.
So, I mean, the Bessel new function would be like, if you just plot it, it will be like a 0 to something.
So if it is K prime P, it is still exponential, right?
It will still be exponential for, yeah, Z goes to one of
Like
them.
In general, it will have form like e to the power, like if you find G from here, it will have form like e to the power pz by z.
I see.
So in, yeah.
It'll be exponentially decaying.
Didn't you choose your G to be a Gaussian at some point?
G.
I thought there was e power minus p square as G, or maybe some previous slide.
Sorry.
When you initially, you chose
like,
K, right? K
Oh,
to
maybe
be
yeah.
a.
First,
K.
it is like when I showed this,
Oh, that was
this
K.
K.
Okay.
Yeah,
First
I mean,
it will
it
be
is
like
similar,
this.
the cutoff function. Yeah, you can.
Then when you're writing Polchinski equation, it is like K prime P square. So from there, G dot is coming.
Sorry, doesn't your action tell you what G is? Like your G isn't it
Action.
P square or something?
No, it will depend on what operator you're choosing. Yeah, that's what like, see, we are putting constant here. So that is a, yeah, with that we will determine the form of 1 by F at low energy, because I already know boundary operator dimension. Okay.
How you what's in a Gaussian fixed point, you get different dimensions for the scalar.
How you cut off? Can you repeat
So
again?
K decided how you cut off the
Yeah,
unit
yeah.
box.
Yeah, that will depend on, yeah, that will like cutoff function depends on Green's function, and that will depend on dimension of the boundary operator. That's
But
what
we
you
were
are
on a
asking.
Gaussian fixed point, no?
What? Like suppose you choose some operator phi or phi square, your G will be up dependent on dimension of phi or phi square, some p to the power some 2 into delta. So it will just this 1 by F will be dependent on that delta. Is that your question?
No, I'm confused. What's the dimension of this boundary scalar in this in the Gaussian fixed point? It's not d minus 2 by 2.
Yeah, it is like, okay,
it's
this you
delta,
have to
right?
find.
I'm just trying to understand how did we get a freedom to fix this mass?
If you, yeah, the freedom that will depend on how you're writing the action. If you take only phi, then this nu will be like, I think not d minus d by 2, but something like Fourier transform of that. And if you take phi square, that is a complicated ERG equation. Their nu will change according to that.
Oh, okay. This is a thing for a phi or phi square or anything. It's not just the phi.
It's for
Generalized free.
Okay.
Yeah.
Just considering a generalized free field or something for a general new.
The confusion is why should it obey a composite operator in general, not obey a
Gaussian fixed point.
boundary?
Yeah.
It won't have a
For
Gaussian.
composite, you need different Polchinski equation, like not this one. Like
Okay.
you perturb with that I will come. Instead of
So what is this freedom of M in the boundary? Like in the starting point, the Gaussian action we started, the M came from the freedom to choose K, right? the M freedom in the bulk mass.
I cannot hear properly.
Okay, sorry, the freedom M, the final solution for the F, which
Yeah.
is really G or K.
You're talking about M, right?
Yeah.
Yeah.
What is that freedom in?
That is fixed by nu. Whatever you choose boundary, it is fixed by that. That's what happens in ADS-CFT. You have a boundary and then corresponding bulk mass is fixed, right?
But boundary, I mean, there is a two things. One is the low energy property, right? And then the cut.
Yes.
So those should be recovered.
Yes. Like low energy propagators can be recovered from 1 by F.
M freedom was not. So I was asking based on K, is
Yes, with this 1 by F, yeah.
based on how it is cut off, it becomes different Gaussian.
See, 1 by F also is related to cutoff. It is related to G, right?
Yeah, that's the problem. I mean, if you have boundaries, you can say doing RGR.
The generalized frequencies are just
The mass is a separate
base of
and
cutting
then
off.
the cutoff is much larger than the mass,
Because K is a UV regulator.
which you use
Different
mass.
IR.
So in that sense, they are not part of the same.
Different dimension.
One comes as part of the cutoff, and the other one is a low energy.
But this mass is, there is mass in ADS only.
Bulk mass.
Yeah,
So what we propose is the boundary. Okay, bulk mass is
boundary operator
yeah,
dimension.
but boundary conformal happens should depend on the cutoff, right?
Yeah, so that's what it should be just a property of whatever the operator. Yeah, operator. Original theory. And so that's right. So that is the question I have in the also. And why is there what did I mean? Yeah, this is a new freedom. It's not there in your it's not there in your original action in other than through the cutoff. Somehow it was some. It shouldn't have to do with the cutoff.
Okay, I understand.
Right. I mean, here the new dependence came because you chose F.
That somehow you have C that you have used also has a low energy connection.
G, P, you are telling? Yeah, G and F is related, so all of them have low energy value.
It has, I mean, is it only a cutoff or does it also have some 2-point function at low?
It's like KP by P square.
So it won't be P square. I think it will be to the 2 nu or something.
Yeah, if that is the case, then it's understood. Right? That's what it is. Yeah. So
It's like, okay, 2 new
P might be like P to the 2 nu.
for anomalous dimension, you are telling. 2 new, okay, sir. Yes, yes, P to the power 2 new. Yeah, yeah. Yeah, that is true.
So that's probably how it is.
the G contains all the low energy information as well as the high.
Yes.
And that's why also the G derivative doesn't vanish. Right? It's not a step function. Like probably knows something about the low energy.
So I would think that the G is equal to 1 over P to the 2 nu into some cutoff.
Which will have a step function.
Which will have
It should have e to the power minus EZ, something like that.
yeah, some or e to the minus P square.
But it's first approximation, yeah. It will have a like complicated form, only low energy it will become like that.
Sorry, but the action was 5 by G, right? So in that you're saying G is
1 over P to the 2 nu would be the free field. Not, yeah, it would be the
Elemental.
higher probably for a field of dimension u.
So what is the problem? You are telling that G is fixing all the.
We had earlier said that G was more like a pattern, right? So G should at low energy, then G should have no. Right? But somehow it seems that now at low energy also, how we have what power of T is inside. Right? Ideally, one to take out the power of T, which will anomalous values. And then define H, which is purely a pattern. Right? It goes to one at low energy and then it falls to exponential. But your G problem is not like that. It's the full G. Full propagator. G of T has non-trivial dependence that goes.
No. Yeah, okay. Yeah. But from
RG cannot apply on correlation function instead of action. Why?
you can apply it on generating function, yeah.
Okay, yeah. So this thing probably is about like generating. Then it makes sense. Default function of two fields could go as be some non-trivial part. To get it from an action on the form phi, you phi is problem.
Okay, are you then actually okay? Then we have to consider ZJ. Yeah.
Yeah. To apply it on ZJ, it's probably much easier to understand what's
That is related to whatever I thought is the standard or alternate quantization. So here we are using mapping to the phi itself. In CFT, we are considering the elementary scalar field itself. If instead of that we consider source, then it is so we are doing it in alternate quantization. But I am not sure whether in other one it will be easier to understand.
Yeah, is there the one that write an action where you have phi minus and then some non-trivial part. That's the one. One function is generating function is fine. That's what they have to work.
But for generating functional also, this same thing apply, like same thing comes, like it comes like this only. For free theory, other things one have to work out. So this comes as it like. Oh, okay. Okay. Yeah, one. Full generating. Yeah, that actually the free theory has been done in Bala's paper, and I think it whenever calculation is easier, go to that side. It is like that. Okay. Okay, so from form of 1 by f, we can determine m of the. So depending on Green's function in the boundary theory, we can determine what is the m square which is allowed by ADS-CFT. So this is the grasp of the process. So once we have ADS action, then correlators can be calculated in standard way. Because we are already starting from boundary theory, and so we will get boundary correlators automatically. So though this is a simplest case, this forms the basis of vector and tensor calculation that has been shown in these papers also before. Okay. Now I will talk about how to derive gauge motion in ADS. Okay. So first I would like to tell what is the key points and result. This boundary conserved current is expected to get mapped to massless gauge field in bulk. So what we have to do is we have to find action for boundary current using concept of auxiliary variable and ERG, then find the ERG equation for that Wilson action of the auxiliary field. So mapping to ADS procedure is same as free scalar case. Now that there will be D scalars, one extra field redefinition because of presence of space-time index. Specifically, we will derive this following equation, which has already been derived in Kawat et al. This EO equation of motion. So this is a scalar field equation with m square 1 minus d consistent with ADS CFT. So upon this change of field variable, one recovers source free Maxwell's equation. Okay. So first is how to form action for composite operator, how not to deal with the composite operator. So whenever we consider a composite operator, suppose J mu is phi del mu J phi J, phi del mu phi, consider this partition function. Then as we flow to low energy, in ERG usually composite operator is defined by linearized perturbation. Like suppose we start with some operator at Bayer theory, which contains phi, which is phi L plus phi H. Then you integrate out the phi H. So whatever is remain, that is given as O lambda. That means like you perturb Bayer action with some perturbation which is proportional to epsilon, and then whatever operator in the Wilson action, in the new scale action you are getting, which is proportional to epsilon, that is given by O lambda. And this O lambda is composite operator at scale lambda. So this is the usual way people do find composite operator in ERG. But this is not suitable for this purpose. Because if one insert only one time composite operator and find the correlators, that can give back correlators of Bayer action. But if you consider more than one insertion, that cannot give back the Bayer action. So here we would always like to get back original Bayer correlators in the boundary at any point of scale. So for that we have to find a suitable quantity which can give back these correlators all the time. So in that purpose, we will use auxiliary variable. It's a dynamical field, but no kinetic energy at T level. This is just writing the partition function.
Sorry.
Yes.
Can I ask a question? Yeah. So when you say that it doesn't reproduce the bad correlators, what do you mean? That if these operators are well separated compared to the things that you integrated out, it should work, right? At least in some approximate level.
No, this is not equal to 0 in general also.
But they should be approximately equal when the operators are well separated. No?
No, it is not. Like why you are telling approximately equal? In what sense?
Like, I mean, if I kind of like integrate out stuff and let's say write down some current operator, right? I should be able to use that current operator at long distances to calculate correlations of currents.
Yeah. So this O lambda is find in a different way. So this is not correct current operator. That's what I am trying to tell. So this does not represent these correlators because this you are founding by linear perturbation. So that's why we are introducing this auxiliary variable, which will just take account whole thing, not the composite operator at like.
But they did the O lambda and OB just differ in some very high energy peaks.
Yeah.
So
Difference should be only 1 over lambda square.
yeah.
Some K, okay, some cutoff, some function of cutoff.
And if these O lambdas are well separated, they are very good approximations for OBs.
Yeah.
For calculating correlators.
Yeah, that you can tell. Yeah. 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 But this is a precise like general statement. Hmm.
Okay. So, okay, so the statement is that if they're far away, like you would reproduce that this is equal. The corrections you are going to introduce would make this exactly equal, but they will vanish if the operators are separated far away. Is that?
This will probably come with some multiplicative factor, like some KP or some cutoff function, some multiplicative factor of cutoff function.
Which then will go to 1 or something far away, or for small momenta.
More, that might be. I haven't checked.
Will it go as 1 for lambda for large? For the left hand side.
See, for large lambda, you are telling, right? Large lambda, it will just go to like continuum theory. So that this composite operators, no? Sorry, that will.
Less quantity is like Q1 minus whatever, Q1 square by lambda square. So yeah.
Yeah, in large lambda, other things will drop out. Yeah. Like.
Other small q or not?
Either small q or large lambda. You have to go near. Yeah. Yeah. Like this O lambda will typically, suppose you are considering phi, it will have some form like del S del phi. So if you take and it is proportional to some Kp. So if you take large, so small p, then it will become 1. It is like that. Like when I wrote Polchinski equation also, like I told that this is number operator, composite number operator. So when you go to low energy momentum, these things will not work. Only this part will work. It is in that sense. Yeah. So we introduce auxiliary variable, which is nothing but we are incorporating a delta function. Both sigma and chi is auxiliary variable which we are integrating over, and then ZA mu we can write it in the following form, where this will be our new quantity which we will be interested in. Because of this form, one can always find their correlators from this e to the power s lambda mu. So you can see this is just like Fourier transform of Z, and from Z one can always find their correlator. So e to the power s lambda is our candidate for finding ERG equation. So this is one problem which one can bypass by considering e to the power s lambda s sigma mu. Still, we have put sigma mu as phi del mu phi. So this is also not. This is also like a Bayer theory. You can tell this is a Bayer theory expression. If you change your scale, this expression will also change. So this quantity will it will be conserved in their theory, but you go to higher scale, you need more terms you have to add in order to form new current so that it gets always conserved. So for that, we have to choose sigma mu such a way that it satisfies conservation law at all scales. For that purpose, we are defining an external gauge field A mu to gauge the ON symmetry, where this d mu is defined in usual way, and this is anti-symmetric. And then define current as this way. If we define current as this way, due to gauge invariance of Z d mu, this will always satisfy conservation law, like del mu of expectation value of sigma mu will be always 0, or 2-point function of like del mu of sigma rho sigma sigma rho sigma, 2-point function of current, that will also satisfy conservation's law. So that's why instead of taking phi del mu phi, we will take auxiliary variable as this. So these are the two inputs we have to put for gauge Boson. Okay, if one does that, next is we have to find Polchinski equation. So first is del mu sigma mu is 0. So we are considering conserved current.
Hello. So
Yes.
when you kind of gauge the scalar charge, you should also have a double A mu term, right?
Yes, yes, that will be there.
But it's not there in these equations.
There will be here, no? It will be here,
okay.
right?
So you're saying you will, okay. And, but so where did that come from here?
See, A mu, so for actually, where did that come from? Like I am putting this by hand,
Okay.
but this A mu will correspond to some potential term in
Okay.
bulk.
So you're saying, you know, like you make it covariant, and that is how you're gauging it.
Yeah.
That is how you're putting the
Yeah,
sources. Okay. And what are you doing it in the sigma chi? If you go back to the previous slide. So here there were no quadratic A mu terms here.
Yeah, there was no, yeah.
So what would you do? You would just change the del mu to d mu, or what are you doing in this way?
See here, here if you like, if you actually try to find sigma mu, that will have this term plus some extra terms, so that all the correlators change such a way that conservation law is satisfied.
Yeah, but I just want to know, how did you modify this action, the first equation, first exponent?
This one you are telling?
The full exponent, how did you put covariant derivatives here?
Yeah, so this one, like instead of putting delta function, so this term will be there also. And here it is new, like their double A mu term.
So I'm assuming that the del mu phi I, you convert into covariant derivatives. Right?
Del mu phi, yes, yes.
But what did you do with the derivatives of phi appearing in multiplying chi? Did you make that also into covariant derivative?
No, we are writing this in that form. So this will have some A mu into phi del mu del phi. So that will automatically come from that term. It's not that we are going from here.
But does the chi couple to A? This is what I want to know.
Chi?
Does the chi couple to A?
Yeah, there is, yeah. Chi coupled to, yeah, if you use this definition, chi will, from this delta function, chi will be there.
No, does the chi, is there a term like chi A in the exponent?
Previous slide, I think what you guys saying is that there should have been a term which is quadratic in AU. And you can either have it by having some term which is quadratic in sigma, or maybe you introduce sigma term, then that would probably have maybe if you introduce a quadratic term
But you probably want the action itself to be covariant, right? Probably, because or else you will have to put a gauge transformation for sigma and chi.
Yes.
I mean, sigma is that is not clear.
In the sense that the current phi I and phi j, that is
That is not gauge
that's
invariant.
a ON.
So the thing that is confusing me is that this action you've written down is not gauge invariant. But the action you write down here starts becoming gauge invariant. So what happened in between? That's all I'm asking.
Okay, so according to me, we are not going from here to, we are just considering like this, because there will be one term like mu phi del mu j, and you are telling that I should able to derive this from this one, right?
Or else what is the point of this equation if you're not using it to derive that? Or else I missed the point of this slide.
Oh, point of this was to show that this is not a correct action to choose, because we need to consider this kind of quantity. So
Okay.
this is not a correct action
So
actually.
you're saying this is not correct.
So how not to? Okay, so I told that. Oh no.
Okay, fine. Okay, so the statement is that what you're saying next is correct. Actually.
Yeah, this one is correct.
But then how does the sigma come here?
Sigma will come like here. You will put constant like this.
Oh, okay. So in this way of writing, there is no chi yet. You have just written sigma now.
Chi will be there if you put this delta function.
Okay.
Again, chi will come.
But not yet.
Not here.
Okay.
But I haven't written all those details actually. Okay, so in order to find Polchinski equation, first we note that we can choose all the variables as transverse. Like because of current conservation del mu sigma mu 0, z de mu is gauge invariant, and chi mu we can choose So we are choosing all these three variables as transverse. Now we want to map sigma mu to gauge field in the level of k tar. Hence, we are putting mu as 0, and we'll find ERG equation for S lambda sigma mu instead. So Polchinski equation for ON model is given by this expression. Okay, where S lambda phi L sigma mu denotes phi h has been integrated up to scale lambda, and sigma mu is like an external field. And for simplicity, one can evaluate phi L is equal to, evaluated with phi L is equal to 0. In order to get physical results, at the end, one need to put lambda is equal to 0. Okay, now, so from this Z A mu, from this expression, one can find e to the power minus S lambda and write the Polchinski equation come from in this value. Where we have make this, what we have done is, we have collected quadratic term in chi mu, and we have noted chi mu is delta of delta sigma mu in first order approximation. So in momentum space, it takes this form, the first order, like leading order. And because these are all transverse, this I mu nu takes this special form IQ delta mu nu. So leading order solution of this equation is given by this. We need evolution operator, which is given by this expression, which is, if you can see, it is same as what was in scalar, but now we have mu indexes, ij indexes. These are like, you can tell d number of scalars. And sigma mu I have following boundary conditions. So rest of is same as what we did in scalar case. So we do take the action, Euclidean action as this, then use the same 3-step procedure as scalar case, and we can write expression like this. Now in this action, if we choose this constant 1 by f, and with this constant of nu square is equal to m square plus d square by 4. Now we know what will be the G dot, G, because this is a boundary conserved current at low energy limit. From that we can get nu is equal to d minus 1 by 2, hence m square is 1 by d. So from this action one can find this is the EOM of the action, and this is exactly what Kabat et al. They derive in their paper. If one does a variable change, as I said earlier, if one does a variable change like this, one recovers source-free Maxwell's equation.
Can you clarify in the boundary and in the bulk, what gauge are you working in?
Yeah, so in boundary it is current conservation, and in bulk it is bulk you are like Az is equal to 0, and then
So
mu.
are you also
Del mu.
imposing del mu mu equal to 0 for
Yeah,
the
del
boundary
mu
source?
mu. Yeah. Del mu mu 0 and Az 0 in the bulk, and in boundary current is conserved.
Okay, but that's given.
Sorry. This mu is proportional to current. It's not same this mu. Like some quantity it is proportional to sigma mu. So in boundary we are taking this del mu sigma mu as 0, and then in bulk we are taking a quantity, suppose small mu, which is proportional to sigma mu. So Az of that is 0 and del mu mu of that is 0. Not this mu.
Del mu of the boundary mu is 0. I think that there's a confusion of, because you're using the same A for bulk, bulk of the boundary.
Yeah, actually, maybe I should call it current C mu. Yeah.
No, that is a different thing, right? You know, bulk mu, boundary mu, and then boundary current. These are three different objects, right? So when you say three variables can be chosen to be transfers, what are you saying? Which three variables do you have?
Sigma mu, then A mu, and then chi mu.
So the sigma mu, A mu, and chi mu.
Hmm.
You're chasing all their divergence to be 0. Is that what you mean by saying using them all to be transfers?
Yes.
Okay. So basically, then you're setting the boundary A mu to be in Lorentz gauge.
Boundary A mu?
It's in the Lorentz gauge. Right?
Yeah, Lorentz gauge, yeah.
Okay. And the bulk A mu is in the radial gauge. Az equal to 0.
Az is equal to 0, yeah.
The calligraphy, okay. Different A.
Yeah.
Z equal to 0. Is there a way to get a general gauge solution without gauge fixing? So you're arguing that it's a map where you gauge fix in the bulk and gauge fix in the boundary, and there's a map. But
we haven't
without
done
gauge fix.
Yeah, this is gauge fixed version only. Yeah.
But can you do it without gauge fixing? Is there a way to do it?
I haven't done, but yeah, maybe I haven't thought of. Like I haven't thought about the process. So this, this actually ends, comes to ends of my talk. So actually in similar way, one can find bulk graviton also. So if one considers mapping of conserved EM tensor to gauge fixed, one can find gauge fixed bulk graviton action. So in boundary, conservation and restlessness of EM tensor is considered. In bulk, we are choosing this gauge AZM is 0, diffeomorphism invariance and restlessness of graviton. So here also one can define an auxiliary variable sigma mu nu and map the radial action to equation of scalar fields. So here each one will have mass 0. This is the same process. So here comes my future. Yes.
You can fix chi mu to be transverse, is it?
Yes.
But wasn't chi mu the gauge transformation of the?
No, chi mu was the variable which we were choosing just to define the delta function. So that we can choose according to. It's on us actually.
But
Yeah,
wasn't
this
it like the gauge transformation of the bulk chi mu?
gauge transformation of the chi mu is just this here. This is just a variable you can choose.
Chi mu is only a boundary field, or is it also there in the bulk?
Here it is. Yeah, it is boundary field. We are
Only
starting
boundary?
from boundary. Yeah.
Okay, there's no. So that delta function with sigma and current wasn't there in the bulk also. Okay.
Yeah. So you can tell that. See, you can try to map like chi mu. So what we got here is we got quadratic time in chi mu, and then we use this approximation. So in first order approximation, sigma and chi is same, but after that there will be like chi is it's chi. So, but you can map this to like yeah, chi is a boundary field. Yeah. Maybe I didn't understand the question. Okay, so the future directions is like this is the simplest level of action one have found. Immediate work is to extend the interaction in case of graviton and gauge field, and equivalent work has been done for scalar composite operator phi square or phi 4 theory in ON model by in this paper by Bala, where in next order cubic potential term in ERG appears, which gives expected correlators according to ADSCF. So if you consider interaction terms, this Polchinski equation will have some term which will have potential terms like potential in sigma. So that you can try to go to see that how it can be interpreted in bulk side. And with this thing, one can try to make connections. Already Vasilyev's paper have prediction for these things in bulk theory. And it will be also interesting to see how bulk locality arises in the scheme. And then another question is, can one extend the scheme in DSCFT? Because here also presence of Poincare like patch is there. And another interesting question can be that we are using interpret holographic RG using boundary RG. Can one do, instead of exact RG, do something equivalent in dimensional regularization and find some interpretation of holographic RG? So that ends my talk. Thank you for listening.
Thanks, Semanti, for the talk. Is there any questions?
Just about this concluding thing, I mean, in fact, if you don't have higher spin gauge fields in the bulk and higher spin fields in the bulk in general, not gauge, maybe massive fields or something, this whole calculation doesn't make any sense, right? Because on the boundary theory, you have some free scalar, which will have all the descendants and everything. And also, like it'll have composite operators and everything. Unless you are kind of, and you need to have analogs of that in the bulk if you want to especially start doing interactions and so on.
Yeah.
Right. So the question is that, like what does one learn just from the quadratic mapping? because at the quadratic level, one has only basically the dimensions, like only the
Yes,
spectrum,
yes,
the
yes.
delta on one side and nu on the other side, and you have some quadratic action, and if you also declare that the mapping is also you're going to design it, that you're not going to derive it, but you're going to like fix it so that you get the answer you want. Okay. As a broader philosophical question is what does one learn from this exercise?
The broader philosophy is like this ADS, like that is like you are like deriving predictions of ADS-CFT, but without using ADS-CFT, you can look from everything from ERG perspective.
Yeah, but in some sense you're putting it in, right?
Yeah,
So
that
it's
is
kind
true.
of cheating, because in the sense that you know what answer you want to get it, and you kind of fixing
Yeah,
it
but
so
that is the point. Like we can see, means ADS-CFT is nothing but ERG. I don't know like what that is a bold statement or not, but it's like you can look at ERG and you can tell what ADS-CFT also can predict.
but and you think that these interactions, for example, when you think about gauge theories and so on, they're like you have to worry about gauge invariance much more.
Yeah,
because,
yeah.
like when you have
Yeah.
interactions and so on, and especially if you have a non-abelian gauge field,
Yeah.
you have very specific interactions in the bulk which are basically governed by gauge invariance.
Yeah. Actually, that is being done by one of my collaborators.
So you're saying that it can be done, and it has been done already, or
it is in process. Yeah, trying to do. They are trying to do.
okay.
Is there any questions from the online participants? If not, yeah, let's thank Semanti for the nice talk.